Hello, my name is Thomas. I am a lecturer in mathematics at the University of Leeds, and in this podcast I want to tell you about a method for solving ordinary differential equations. This method involves the expansion of the function y of x, say, into a power series, and that's why we talk about series solutions of ODEs. What I want to do is I want to talk you through the method using one equation and use an example to show you how it works. If we want to solve a differential equation, then we have to go through certain steps. And one of the most important steps, if not the most important step, is to determine the type of differential equation. Because once we know the type of a differential equation, then we can maybe use a method that is suitable for this type. And you know a few examples for this, hopefully. If we have a first-order differential equation of the form y prime is some function of x times some function of y, where y prime denotes the derivative of the function y, then we can solve this equation or try to solve this equation using the separation of variables. If, on the other hand, we have a second-order differential equation, a times y double prime, so the second derivative of y, plus b times y prime plus c times y is equal to 0, then we can compute the roots of the auxiliary equation and can obtain solutions for the differential equation from those roots. But now what happens if we are given a differential equation that doesn't fall into one of these types, one of these categories that we have a method for? Well, the method of using power series allows us to at least approximate the solution in this case. Series solutions are a very general method for solving ODEs, or if not solving them, at least approximating the solutions to a desired degree. The idea is quite simple. We expand our function y of x, the function we are looking for, in a power series. This is nothing else but a series, so an infinite sum if you like, an times x minus x naught to the n, where n goes from 0 to infinity. The variable in this series is x. There are two more numbers in there, or in fact infinitely many more numbers in there, but there's the variable x naught. Now this is a number we are free to choose, and we will see how to best choose x naught in a minute. And then there are the coefficients an. And these are the ones we actually want to determine. So what we do in the following is we take this power series, plug it into our differential equation, and then we get a system of equations from which we can determine the an. Now, you see that y of x is a series, so it has infinitely many coefficients. So this system of equations might not be very easy to solve because it has infinitely many variables in it. But we will see how this goes in an example. Before I start with the example, I thought it might be a good idea, though, to see why we can actually write a function y of x in this form. So let's say we have an arbitrary function, y of x is sine x, or y of x is log x times 1 plus cos x. Without thinking about it, it's not clear at all that we can write these functions as a power series. But there is a theory that allows us to do this, and this is the theory of Taylor series. So let's just refresh our memories and see what Taylor series are. If we are given a function y of x, which can be differentiated often, ideally infinitely often, and if we choose a point x naught, a particular x value, then we can write down a Taylor series, t of x, for this function. And the Taylor series has the following structure. We start with the function value y of x naught, so the function value at this particular point, and then we add the derivative at this point, y prime of x naught, and multiply it by x minus x naught. Then the next term we add the second derivative, y double prime of x naught, divided by 2 factorial, and multiplied by x minus x naught squared, and so on, so that the nth term in our series has the form nth derivative of y at x naught, divided by n factorial times x minus x naught to the n. We can write single terms of the series, or we can also use the sigma notation, so that we can write it as a sum for n from 0 to infinity of the nth derivative of the function y at x naught divided by n factorial times x minus x naught to the n. And you see that this is just a power series, where the coefficients an are given by the nth derivative of y at x naught divided by n factorial. Now I want to point out two particular coefficients because they will be of importance in the following. If we look back to our series, to the single terms, then we see that the coefficient a naught, This is the one that doesn't have any x term. It's just the function value y of x naught. And the coefficient a1 is just the derivative y prime of x naught. We will return to this later. So that's the formal definition of a Taylor series, but what is it actually good for? Well, let us have a look at one example, which is a classic example in this context. Let us take a look at the exponential function e to the x, or exponential of x. I choose the point x naught to be 0. In this case, the series is also called a Maclaurin series, but we don't really have to worry about this. If we want to write down the Taylor series of y, we have to compute all derivatives of the exponential function at the point x naught is equal to 0. Now, thankfully, this is not very hard, because the derivative of the exponential function is just the exponential function again. This means all the derivatives at 0 have the same value, and you know that the exponential function at 0 takes the value 1. So y of naught and all derivatives of y at x is equal to 0 are just 1. And now we substitute this into our general formula for the Taylor series, and we find that t of x is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on. We can now, of course, just consider finitely many terms of this Taylor series, say the first n terms. Then we get the Taylor polynomial of degree n, and we see that these polynomials approximate the exponential function as n increases. On the graph on this slide, you see the exponential function in blue. It is actually quite hard to see, because there is something plotted on top of it. And then you see a few polynomials. The one at the bottom, the straight line, that is just a linear approximation. So the first two terms in our Taylor series, which give the tangent vector. The slightly darker gray one, the parabola, that's the quadratic approximation. So the first three terms of the Taylor series, so it would be the Taylor polynomial of degree 2. And then I've plotted a few more. You see that there is a line almost on top of the blue line, which is a Taylor polynomial of degree 8. So already then we have a very good approximation of the Taylor polynomial with the function exponential of x. In fact, it turns out if we take the limit n to infinity, so if you consider the Taylor series, then this Taylor series gives us precisely the exponential function. So we can use this series as a new representation, or a new definition, if you like, for the exponential function. And this is the reason why we can use power series in order to find solutions of differential equations. The same method works for many, many functions, not for all of them. This is quite a subtle question. But if we can represent a function as a power series, then of course we can try to find a solution of an ODE as a power series. So let's see how this can be done. I now really want to solve a particular ordinary differential equation, just to show you how the method works. I've chosen the following example. The differential equation is given by y double prime, second derivative of y, plus x times y prime plus y is equal to 0. And I also have some initial data. At the point x is equal to 0, I want y to be 1, and I want the derivative y prime to be 0. So this is an initial value problem. Our equation is a second order differential equation, because we have a y double prime. And it is actually linear, because y and its derivatives only appear in linear combinations. However, for this equation we cannot use the method of using the roots of the auxiliary equation, because we have a term x times y prime. So we have a non-constant coefficient in front of one of the y prime terms. Well, we don't have a method for solving this equation, so we try to find the solution as a power series. Our initial conditions are given at the point x is equal to 0. So remember, in general, our power series was of the form the sum of the an times x minus x naught to the n. Now, if the initial condition is given at 0, then a good choice for x naught is equal to 0, which means that we look for our solution y of x in the form the sum n from 0 to infinity an times x to the n. And now we have to substitute this power series into our differential equation. On the top of the page you see the formula for y of x again, our power series. I've written down the few first terms of the series as well. And now we have to differentiate this series twice. because it's a second order differential equation. So let's do this in steps. If we differentiate y of x, this means we can differentiate the power series. We can simply just differentiate the single terms in the power series. So let's start with this before we look at the sigma notation. If we differentiate a naught, then we get a 0 because it doesn't contain any x. If we differentiate a1 times x, we obtain a1. If we differentiate a2 x squared, we obtain 2a2x, and so on and so on. And now we can write this again using the sigma notation as the sum where n now goes from 1 to infinity, n times an times x to the n minus 1. So this is the first derivative of our power series. For the second derivative of our power series, we have to differentiate this again. And let us start again with the single terms rather than the sigma notation. If we differentiate a1, we get a 0. If we differentiate 2a2 times x, we get 2a2. If we differentiate 3a3x squared, we get 6 times a3 times x, and so on and so on. And we can write this as the sum for n from 2 to infinity, n times n minus 1, an times x to the n minus 2 now. So we've got all the derivatives in our differential equation, and now we can just form the equation again and simplify it a little bit. The equation was y double prime plus x times y prime plus y0. So we get the first line on the slide. And in the middle term, x times the sum from 1 to infinity, n times x to the n minus 1, we can simply multiply in the x. And so this sum becomes n from 1 to infinity, n times an times x to the n. So now we have an equation that involves 3 infinite sums, which is not very easy. But we can use a very important principle to actually solve this equation. If you look at the right-hand side, if we were to simplify this further, then we would get a power series in powers of x with some coefficients in front of it. And we want this to be 0. And this means it should be 0 for all x, because the differential equation needs to be satisfied for all values of x.